at because Allison ended on this note, whether if there are spirals in these young disks, then why don't we see them? And through this talk, we have one potential reason why we might not be able to see them. But yeah, so I'll be talking about warps in dusty self-gravitating protoplanetary disks. And Sal has set up the stage for me very well because he's already introduced warps, he's already introduced GI disks, so I can jump straight to the science part of it. And um, we care about protoplanetary disks because they're the birthplaces of planets, and whatever happens in this phase will leave imprints on the kind of planets that forms, as well as the architecture of planetary systems that form. And this figure was already seen yesterday, and it received its fair share of criticism because the process is more complicated than this simple picture. But yeah, the main point from this is we care about it because it has an imprint on planets. And we expect these signs to show these disks to show signs of a self-gravitating phase in young disks especially. So we have L144 at IS3b, which is a triple protostellar system, and we see this spiral arm coincident with the protostar. Oh, is my mouse also visible?
Yes.
Perfect, thanks. And we have ABR Gay, where we have all of these spiral arms. We've seen this figure before as well. And then Lias 27, where we have these gaps intersecting with these ring-like features. And so we have signs of a self-gravitating phase. And previous simulations in the self-gravitating phase of warp disks by Sal have shown that when a warp is introduced in a disk, it can form these axisymmetric structures. So this is a disk, and here we have warp. As we let the disk evolve, this warp heats up the disk, and then we get an axisymmetric disk with ring-like features at the end of the simulation. And so yeah, we have ring, we have the spiral structure is suppressed, and if we let it run for even longer, the spiral structure comes back. Now, the question I'm trying to ask is what happens to a gravitationally unstable dusty disk when a warp is introduced? So these were gas-only simulations. What would happen if we introduced dust into the mix? And so to do that, I've performed simulations with Phantom. I've taken a star mass of 1 solar masses, a disk mass of 0.1 solar masses. The dust to gas ratio is 1:100, and we're taking a one fluid simulation with two dust grain sizes, 1.4 mm and 1.6 microns. And we made these choices in case we want to perform synthetic observations or anything. These sizes would be relevant to what we can see with ALMA or JWST for that matter. And then we are using beta cooling with a beta value of 15. We explored the similar misalignments that Sal explored, so 5 degrees, 15 degrees, 30 and 60 degrees of warp misalignments. The radial extent of the disk is from 3 AU to 80 AU, and we're simulating this with 2 million particles. So let's jump right into the results. This is we have 4 cases of misalignments, but for this talk, I'm just showing one. In this disk, we have a 30-degree warp, which we can see at the start of the simulation. And as the disk evolves, in both gas and dust, we see these axisymmetric structures and this formation of ring in the outer edge of the disk. And as the simulation evolves even further, the spiral structures begin to come back. And so now the question is, why is this happening? Why does the disk become axisymmetric, and why do we see the formation of these ring-like structures? And whether or not a physical warp is significant for that kind of thing to happen. And so we look at the CS and the doomed parameter plots. So in the top panel, we have the sound speed versus the radius. In the bottom panel, we have the doomed parameter Q versus the radius. And we see the evolution of the disk from 0 orbits until 6 orbits. Just to note, when I say 0 orbits, the disk was already allowed to evolve so that it could develop these spiral features. So the spiral structure that we saw at the beginning of the simulation, and that is the point where I mark this is t equals 0 orbits. But the disk was allowed to evolve before that as well. So yeah, as the disk evolves with a warp, we see there's heating happening in the disk, and correspondingly, the tumor parameter increases as well. And if we look at the surface mass density, there are no big changes in surface mass density, but in the outer edge of the disk, in both gas and both dust sizes, we can see this bump, which corresponds to the location of our ring. So now we have the CS and the Toombs parameter, and we ask the question whether it is the physical warp that is causing this disk to form these axisymmetric structures, or is it actually the change in temperature, the heating of the disk, or in general, the change in the Toombs parameter. And to answer these questions, we perform control tests. So our first control test would be by varying the cooling rate in the disk. And in for a disk with beta cooling, this would typically look like du by dt is equal to minus u, and this would be omega by beta. But we modify this to have a delta beta parameter. And these are the four heating profiles that we explored. So the first is a symmetric Gaussian, the second one is a skew normal distribution, the third one is a double Gaussian, and the fourth one is an asymmetric Gaussian. And we change the beta parameter so that we can model all of these profiles. And what we're basically trying to do by seeing all of these different heating profiles is see how close we can get to this heating that was introduced by the warp. Because when we're asking the question whether it's the physical warp or just the heating that's causing this change, we want to model the heating as close to the warp case as possible. And so we found that the double Gaussian case was the one that was closest to warp-like heating. And so in our first test, where we vary the cooling rate, these are the results. So we again start with a spirally disk, and as the disk heats up without the presence of a warp, we see that the disk again develops this axisymmetric structure. So heating can result in an axisymmetric disk too. What about if we reduce the disk mass? Because the Toombs parameter depends on the sound speed, yes, but also on the surface mass density. So if we reduce the disk mass, then the Toombs parameter will again increase, and we will be able to answer the question whether it is a physical warp, whether it's the heating, or whether it's this generic change in Q that is driving the disk to form an axisymmetric structure. And so we do this performing three tests on the disk mass. We reduce the disk mass by a factor of 0.6, 0.4, and then 0.32. And this is done so that we can get the Q values up to certain levels and stabilize the disk. And when we do this, again, we see that the disk is forming these axisymmetric structure. And in the outer disk, especially if I go back here, you can see the ring-like structure appearance again. And so reducing mass can also result in an axisymmetric disk. Now, the way that we reduced mass was using a mod dump, and the mass reduction was instantaneous. So after the disk had evolved into these spiral structures, we introduced this mass reduction. So by whatever factor, let's say it's 0.6, then the disk mass dropped instantaneously from the old mass to 0.6 times the old mass. And then we ask the question, what if this is not instantaneous? Would the same thing happen if we reduce the disk mass over a certain period of time, which is what is happening when we consider heating and the warp? It's happening over a few orbits. So let's decrease the disk mass over a few orbits. And we see in this case as well, the disk forms this axisymmetric structure. And so reducing mass over 3 orbits can also result in an axisymmetric structure in the disk. And so where we are now, a GI disk with these spiral structures becomes axisymmetric with a warp. It becomes axisymmetric when we heat the disk. It becomes axisymmetric when we reduce the mass of the disk instantaneously, and when we reduce the disk mass slower. And I put quotations on the slower because 3 orbits is still fast. And yeah, in this plot, we see the surface mass density versus the radius. And I've plotted this for a number of cases. So we have this pink line is the 30-degree warp. These two are the dust sizes that we had in the 30-degree warp simulation. All the other simulations, the control tests that we did were gas only. So there are no dust for those cases. The orange curve here is the double peak heating. And then two of the highest and the lowest mass that we reduce the disk to are shown here. And all of these show the same bump in the surface mass density that correspond to a ring-like feature. at roughly the same radius here and in the inner region as well. This is all at 3 orbits. So yeah, we see these axisymmetric structures, we see these ring-like features roughly at the same location for all of these different simulations. And so instead of saying that all of these different changes trigger the disk to form these axisymmetric structures and rings, we are now at the stage where we can say that fast changes in the disk's tumor parameter Q drive the disk towards an axisymmetric structure. And again, fast is in quotations because 3 orbits, we have done this over 3 orbits. It is still possible that if we do this mass reduction or heating in slower than this, it could still work, but that remains to be seen. So until now, what do we have? We have rings in dusty misaligned self-gravitating disk. This is consistent with gas-only prior work. So we've confirmed that this happens in the dust as well. And we see that this happens even with the absence of physical warp. Even if the disk is heated, the disk mass is reduced, and if it is reduced gradually or instantaneously. And what we're trying to answer right now is why does this disk develop axisymmetric structure when the disk tumor parameter changes rapidly? And when do we expect things like this to matter? When do we expect this to happen? And then the last thread of this would be whether or not we can observe this. And we would be doing synthetic observations with MC first to figure that out. And yeah, just a potential case where something like this would matter would be weak flyby events. This is just an illustration from Neal et al. 2020, where we have the disk which encounters a flyby and then gets warped. So this would be one case where our result could potentially apply. We're thinking about weak flybys rather than strong flybys that disrupt the disk or truncate the disk significantly. And very recently, we've also been started thinking about whether or not if fragments form in the disk and those fragments go inside the star, if they get accreted or tidally disrupted, then could that actually heat up the disk to, again, get us into a configuration where we lose the spiral structure and go into this axisymmetric state of the disk? And we don't expect these events to be rare, like flybys to be rare anymore. And we've seen versions of different graphs in the talks previously, which talk about disks not evolving in isolation. But I really do like this figure from another conference. This is from Jerezov et al. 2025, and it shows that most of the single systems that they recover, which is around 21% here, they are born bound from birth. So they are born as part of binaries, which then make single systems. And so to think that disks evolve in isolation or that we'd expect these events to be rare is no longer true. And yeah, if I had to leave you with one take-home message, I will just leave you with that self-gravitating disk with dust also show axisymmetric structure, and we don't need the presence of a warp to cause the same effect. It can be due to multiple reasons. And why this happens and whether this can be observed is still under investigation. Thank you so much for listening.
Hey, it's getting late here. We've just been through a hack session, and I think everybody's starting to fade. Oh, we have one question, saving the day. Thank you.
Thank you for the presentation first. That was really nice, and the slides are also very nice. That was objective to follow. I'm asking from the observation side of things. Don't you have any past signatures of your perturb kinematics that you could observe in the gas? Imagine you observe this perturb kinematics and then this asymmetric structure in the disk. Could you say that something has happened somehow, or is it too difficult?
We're not sure yet. We haven't thought about whether or not we can observe this kinematically yet. But when we go into the synthetic observation stage, we will definitely think about it. Thanks for the question.
You? Any other questions?